Okay, so now last time I think you left off at, you discussed the Jacobi generalization, and we came up with an algorithm. In fact, two ways of implementing the Jacobi method. And one of them was essentially to go over, so remember, you're given a system of equations, okay? You're given the matrix, the full matrix, and then, you pick, you're going to build the solution one term at a time. You go over all i's, these are the rows. So you go over x1, x2, x3, and so on, and then you just iterate. So there's going to be two loops over here in this formula, right? The first loop is going to be over how many iterations, and the second loop over all the x's. Okay, and I'll show you the code in a second. Now, just for the Jacobi algorithm, you can write this in a simpler form that doesn't require a loop over the equations or over x1, x2. You can do it in one shot as a vector calculation. Remember, what we do with Python, when we take two NumPy arrays and add them, for example, or multiply them, this is what's happening here. We're taking the entire vector of the solutions and saying the new solution, xk plus 1, the updated guess, is equal to the old guess plus 1 over the diagonal entries only. So the diag A gives you an array or a vector of only the diagonal entries. And you do 1 over that, so it's 1 over A11, 1 over A22, etc. So remember, this is a vector operation. So this is a vector, this is a vector, this is a vector, this is a vector, and AX, K, is also a vector, right? Because A times X, it's an n by n matrix times n by 1 is going to give you an n by 1 vector, okay? Okay, so an implementation of this is as follows. Import NumPy, blah, 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 etc. The Jacobi method, the way I implemented it here, you can implement it in 1,001 ways, okay? Leave that up to Shahrazad. But it's 1,001 ways you can implement it. In here, I'm implementing the Jacobi method. It takes a matrix A, okay? That's the full matrix. We learned how to construct this for tridiagonal matrices, and you can build it for, hopefully it's sparse. Okay, for this method to do well, it's going to take a guess. I'm giving the user the opportunity to provide a guess. Otherwise, I could hard code the guess to be 0. But what if you know more? I'm assuming that you know more about your system. You probably know where the solution is, but not quite. So if you start there, you're closer. Remember iterative error. If you're closer to the solution, you're going to converge there faster. Okay, you're committing less error. So I'm allowing the user to provide a guess. We need the right-hand side, obviously, AX equal B, right? And also we need the maximum number of iterations that we need to carry, right? Because otherwise, how long do you keep iterating? We're going to talk a lot more about that. But right now, assume you give a fixed number of iterations. The first thing I want to do is get the size of the matrix. I did discuss this in the lecture that I recorded, but we'll go over it real quick now. So first thing I want to do is get the shape of the matrix n by n. So, I'm calling it nr and nc for n rows and n columns. And you better make sure that nr equal nc. So if you're a good programmer, you would do error checking over here. You would check if nr is not equal to n and nc, turn off the computer, and shut down the electricity, whatever, right? So you can't operate, obviously, right? But I'm not doing error checking here, obviously. But anyway, that's something you should think of. Then we start with an iteration counter equal to 0. That's a counter. And I initialize my solution vector to be zeros. So x, I call it, be the solution vector, np.zeros of size nr, number of rows. Or you could put nc, it doesn't matter. Now I start my while loop. While my number of iterations is less than maximum iterations, right? Max iter could be 100. Iter starts at 0, so we enter the loop. Now, within the iterative loop, this is called an iterative loop. Within the iterative loop, I'm going to go over every solution entry. So I'm implementing the first algorithm, the first method. So I'm going to go over each one of those equations. Remember, Jacobi method solves equation 1 for x1, equation 2 for x2, equation 3 for x3, and so on. So that's what I'm doing here. For I in range from 0 to n, rows or n equations. So this goes from 0 to nr minus 1, exactly. We solve for x0, and then x1, and then x2, and so on, by using the following formula. xi equal x gas, right? That's the formula we saw, plus 1 over aii. That's 1 over the diagonal entry, if you see the previous formula, right? xik plus 1 is xik, so x new is equal to x old plus 1 over aii times bi minus this fancy summation. This is nothing more than the dot product. Remember, we're going over I. I is fixed here, right? When we entered the for loop, I is fixed. We're solving for xi. You're solving the ith equation for xi. So I is fixed. What that leaves you here is that if you fix I, that sum aij xjk is nothing more than the dot product of the vector, of the row vector of the matrix at I. So if you pick the matrix and take the ith entry of the matrix, it's going to give you a bunch of entries. That's a vector, right? That's a vector. And you dot it with x. So that's the dot product. Gives you one single number, okay? Oops. Okay, so 1 over ai bi, this is clear. This one here, I'm taking ai. I claim that this returns, remember, a matrix has two indices, I and j, row and column. But what if you call only one index, ai? It will give you the entire row. In other words, all the columns that correspond to row I. And it's going to be a vector. So that ai dotted, so the dot product, you can use the at symbol. And this is the first time I introduced this, obviously. So to do a dot product between two vectors, you can use the at symbol. So I'm dotting the row ai with the x guess. Okay? So x guess, again, is xk. Okay? Now, when you do the loop, you loop over all the equations, solve equation 1 for x1, equation 2 for x2, and so on. Once you're done, you update your x guess. Remember, the Jacobi method is a guess update. You start with x guess, you refine it, then we use it. We're going to use that new refined guess in the next iteration. So what I do, I take my new solution and make it a new guess. And then I go to the next iteration, and so on, until we hit a maximum number of iterations. Okay? This code is for you to ponder, to study, to memorize, and to use. Okay? I will ask you, however, to make some modifications in the homework. Okay? In the past, your poor colleagues used to have to write this down from scratch. Okay? Anyway. So here's an example using this system, solving this system of equations. And it's very straightforward to implement. Just copy the code and call the Jacobi method. Anyway, the point here I want to talk to you about is, this is the solution I'm showing here. The exact solution is given there, 0.93, 3.04, and 2.30. That's the exact solution. This was obtained using A inverse, okay? Or a built-in direct solver, okay? Now, obviously, for a small system like this, Jacobi is silly to use. Obviously, we're using this to verify. Remember, we test things on systems we can handle, and then we go to large scale. But what I'm showing here is a table that has the following columns. K is the iteration count. X1, X2, X3 are the solution. So starting with our guess, 1, 1, 1. Iteration 0 obviously has the guess, 1, 1, 1. Now the first iteration updates the guess to 1.63, 2.25. Iteration 2 starts kind of changing the solution, and then you go through, and then what happens here? Why do I have this blue rectangle over here? What's happening to the solution with this blue rectangle? Yeah.
Just getting more significant digits.
So yes, we are gaining more significant digits, or are we? Or not much, not that much. It's kind of the solution is not improving much, right? You hit 0.93, 0.233, 232, 2325, 2325, 2325, 1,000 iterations, doesn't do any better, okay? Now, what is the problem with our implementation? What was the problem with the implementation we just did?
Was it like the max iteration?
Yes, so yeah, elaborate.
So since he
Okay.
Do some max iteration that computes the difference between the
Okay, before we get there. Okay, so let's stick to the idea. What Tyler is saying is, look, how the heck do you know where to stop? You can't test your Jacobi with 1,000,000 iterations and say, oh, the system works for 100 iterations. But you just solved it. And obviously, you don't want to run it for 1,000,000 iterations because in real systems, these are very expensive to solve. It could take you hours. Yes?
So maybe take the approximate errors
Yes.
between things so that it reaches 0?
Yes. But before we get there, let me just kind of get this concept anchored. You see, the problem with this is that we don't know how many iterations we need to take. Right? We don't know. So we need a better mechanism. The way we programmed this, we allowed the user to just specify only the number of iterations. What would be better is a way like something like significant digits or a tolerance. Keep running the solver until we hit a certain tolerance. Now, Tyler and Katrina can talk to us about your ideas of where to stop. So where do you suggest we stop?
So just have some sort of where, just calculate the approximate error.
Okay, between
each point.
Right,
And
okay.
see that and get it close to 0. So say
Or to a tolerance, right? And that was your idea, essentially, right?
same thing. I think you'd have to know what application you're doing because that would determine the tolerance. That would
Yes. Okay. So obviously, using a fixed number of iterations can be inefficient. We need a way to tell the solver to stop the iterations. So when do we stop iterating? If you notice again here, what's really happening is that the computer and all the arithmetic that's built in it, all the calculations, cannot refine your solution any further beyond probably 30 iterations or 35. It just cannot do any better. You are not gaining any significant digits anymore beyond 35 iterations. Okay? So one idea to assess the error would be to look at the approximate relative error, like your colleague said. In other words, hey, new iteration minus previous iteration, what is the error? Just calculate the error between the new iteration and the previous iteration. And what did we call that error? Approximate relative error, right? So we already have a definition for that error. In other words, as we refine our solution, as we get more accurate, keep track of this error. This is similar to adding the terms in the solution. However, this is iterative error, okay? So let's do just that. So I'm going to take this table and compute the error. But there's a problem here. How many errors do we have? You said a lot? A lot? Okay, so let's say for a given iteration, how many errors do we have? 1? No, 3. 3, yes. Correct, because we have, in this problem, we have 3 unknowns, right? x1, x2, x3. And for each one of those unknowns, there's an answer. And each one of those answers is going to commit an error, right? And take iteration 10, for example. The approximate relative error in x1 is 6 10 to the minus 3. In x2 is 4 10 to the minus 2. And in x3, 6 10 to the minus 2. And this would be the same case if you had 1,000 entries. So go back to the heat transfer problem. Let's say you're doing it for 250 points, 250 temperatures. You're going to have 250 errors. Now, my question to you is, which error should we use to judge whether the solution converged? So take iteration 10 again, or iteration 4. The error here was 10 to the minus 1, but the error here, error 0 and 10 to the minus 2. So obviously, one answer or one unknown is converging faster than the others. So how do we pick something that represents the error across the entire solution? Okay? Do you have any ideas? Yeah. Yeah. Okay. Yeah. So other ideas?
So you could pick the one with the largest.
Yes. Yes.
average all the
Yes.
I mean, you could just, if you have a tolerance that you're trying to go for, then if you go, it's not like the highest one is below.
So yeah, that's what Emily said. Essentially, pick the worst error across all the x's, right? Pick the worst one, pick the largest value, and hold that accountable. You don't care if the others converge. What you care about is the maximum one. Yes?
This is kind of maybe a little different, but could you make an equation for the error and see where it'll approach and you know where your memory runs out? And then say it says
But
iterations, could you, I don't know if that makes sense.
I didn't quite understand what you're saying, but still, that doesn't answer the question of how do you get a sense of the error? We have n number of errors, n entries, 250, 1,000.
Can't you like rescale it with like, so like if error 1 was trying to measure that bridge, it's 100 meter.
Well, these are scaled. They're relative, right? They're approximate relative errors. Yeah.
I don't know, maybe put it in like a matrix of sorts?
And then do what with it? So you already gave the answer, and this proves to you that you all understand, you're all mathematicians by heart, and what you all talked about are called vector norms in mathematics, okay? They essentially measure an average sense of the error. Okay, what we're looking for here is, for a given iteration, we want a measure, a sense of what the average error is. One of them could be pick the worst error always. So, iteration 30, this would be your error in this case. It's the worst one, it's the largest one, right? Do you have?
Couldn't we also pick a different error value, a different tolerance for each error?
No, well, but still that doesn't answer the question of when do you stop? Do you pick, we need one value for the error and say that value is less than the tolerance. You're complicating the problem by saying multiple tolerances for different unknowns, but that complicates things. We need something much simpler. We just want to say, hey, run this solver until the tolerance is less than 10%. Okay? So you keep running, you check what is the max error here. It's 10 to the minus 3. It's still greater than 10%, than 1%. Or whatever, 10 to the minus 10, for example, your tolerance, that's a tolerance we use. Keep running until you get here. Well, over here, even that doesn't work because 10 to the minus 9 is greater than 10 to the minus 10. So you have to get here, and then you stop over here, okay? Okay, so now let's formalize this discussion. So together, E1, E2, E3, En, they form a vector, okay? At each iteration, they form a vector. And what we're obviously looking for is some sense of average or a collective measure of what the error is. And that's where we introduce vector norms. So now we're going to step back and talk about mathematics, okay? When you all remember the Euclidean norm or the Pythagorean theorem, what does it tell you? That, a squared plus b squared, right, is equal c squared, right? That's called a Euclidean norm that essentially measures a distance between 2 points. Now, you can generalize this to n dimensions. So if you had a, b, c, d, e, f, g, or a0, a1, a2, an, you can calculate the same Pythagorean norm, an average distance, by taking the sum of the squares of all of the entries and taking the square root. That's one type of norm. But that norm is generalizable. You can define an infinite number of norms. I'm going to talk only about 3 norms. So vector norms, they measure a sense of distance or scale for a given vector. Now think of a vector. Don't think of it as a position vector. Think of it as we think of it in numerical methods, as an array, as a list of entries. In our case, our vector is a list of errors. Okay? So that's a vector with n entries in it. I'm going to introduce 3 norms over here for the vector A. You notice the notation for norms. You have these two absolute values. That's a norm. You have the L1 norm, L2 norm, L infinity norm. The word L comes from, algebra and math. Don't worry about that. But essentially what this is saying, the L1 norm says, just take the sum of the absolute value of all the entries in the vector. So that's similar to the average. You said you just take the average value. And you can probably divide by n. I think it's missing an n. Okay? The L2 norm does the Pythagorean theorem. It takes the sum of the squares of the entries. So a1 plus a1 squared plus a2 squared plus a3 squared, an squared, sums them all up, and then takes the square root. Gives you an average sense of measure, at least when we're talking about the Pythagorean theorem, it does calculate the distance between the 2 points, right? And then the L infinity norm, which is what you talked about, take the maximum value, the worst error that both of you talked about. You take the maximum error or the maximum value in that vector, okay? Is this clear? So that's math. That's just definitions. So now we have a tool, okay, to take at any iteration, we have a vector of errors, right? And the size of this vector is equal to the size of the solution vector. If you had 50 equations, you're going to have 50 errors. Okay? If you had 100 equations, you're going to have 100 errors. Okay? In Python, it's pretty easy to do this. You just call, if A is a vector, you just call numpy linear algebra.norm, and A, and you give it the number here, which norm you want. This is L1 norm, L2 norm, L infinity norm. Yes? It's an array. It's a vector, yes. So now we can simply compute a norm of the error vector at each iteration, and then stop when the norm is below a certain tolerance, okay? It doesn't matter, really, what norm you choose, as long as you choose one. We'll talk about this in a second. But, for example, for this case, this is the L2 norm. For every iteration, takes the L2 norm for these errors. So for iteration 30, it takes this one's E1 squared plus E2 squared plus E3 squared, and takes the square root of those. And that gives you 10 to the minus 7, right? There may be a typo over here. Oh, actually, no, it's correct. So what, what matters here is that you're getting an average sense of the error, okay? Just one number. And then you can say, if that number is less than the tolerance, then stop, okay? And with this, a couple minutes. Okay, so which norm do you choose? Really, it doesn't matter. It really doesn't matter as long as you are clear about which norm you are implementing your algorithm with, okay? In the end, the difference will be one iteration, probably, okay? So for the vast majority of cases, this just works, okay? Now, okay, so yes, with this we can close. Next time we will talk about the different types of error measures. We only talked today, hold on, you still owe me 2 minutes, 1.5 minutes. So today we talked about the approximate relative error between iterations. But there are other errors we can look at in systems of linear equations. Can someone think of just one other? So remember, we're solving AX equal B, right? So if AX is equal to B, then we solve the system exactly. So as you iterate, you can always evaluate A times X and then compare it to B, right? Because we want AX equal B, right? But we don't know what X is. So as we compute X, you do A times X, and then compare that, see how close it is to B. So there are other errors. We'll talk about those on Thursday. Okay? Thank you. See you on Thursday.